guys, today we're going to start our chapter of solving systems of equations. There are three methods that we're going to see and use to solve a system of equations. The first one is by graphing, which is what this lesson will be on. A system of equations has one, none, or many solutions. We're going to look into graphing a system of equations, in which involves graphing two equations on the same coordinate plane, and then discussing how many solutions it's showing us that this system has. Let's take a look at problem number 1, in which we have two equations in slope-intercept form. A solution to an equation is an ordered pair, an x and y value, that when you plug into the equation, you would get a true statement. The left side would equal the right side. A solution to a system of equations is an ordered pair that would be a solution to both. Again, we're going to solve this by graphing, and I'm going to first graph the first equation in pink. I'm just going to put a little pink dot next to it so we know which line is which on our coordinate plane. Since it's in slope-intercept form, I'm going to start with the y-intercept of -3 and plot a point on the y-axis at -3. We'll then use the slope of 2, in which represents the rise over run. From your first point, you're going to rise 2, which means to go into the direction up 2 and right 1, and graph your nice straight line. You're going to want to graph the line for the entire coordinate plane as much as you can, the entire length. The second line I'm going to graph in a different color. I'm going to graph in purple so we could see the difference. This has a y-intercept of +2, so my first point will be on the y-axis at 2, and a slope of -1/2. Since it's negative, I know we're going to be going down 1 and to the right 2. So from my first point, -1/2, rise -1, down 1, run 2. And I'll go ahead and graph my straight line. Again, you want to make it as long as you can to cover the whole coordinate plane. What does the graph tell us so far? Well, if I were to ask you to name me an ordered pair for the first equation, you can name me any ordered pair on the pink line, since I did the first equation in pink. Any ordered pair on this pink line would be a solution to that first equation. If I were to ask you to name me ordered pairs that are solutions to the second equation, you can name me any ordered pair on the purple line. A solution to a system is an ordered pair in which is a solution to both. Do either of these lines have an ordered pair in common? Yes, they do. Since they intersect, they have the ordered pair in which they intersect in common. Therefore, that ordered pair is a solution to both of the equations or a solution to the system. So we would say that we have one solution, and specifically the solution is the ordered pair 2, 1, since that's exactly where the two lines intersect. A system of equation can have one, none, or many solutions. So this is an example of when there's one solution when the lines intersect each other. We're going to now look at two problems in which we'll see when there are no solutions or many solutions. I'm going to move down to problem number 3, and we're going to start the problem the same way, by first graphing the first equation. Since it's in slope-intercept form, I'm going to start the y-axis at 2 and use the slope of -2 to make my second point. Since it's negative, I know I'm going to be going down 2 and right 1. Just like the first problem, I'm going to graph the second line in a different color so we could tell the difference. I'll graph that one in pink. That one has a y-intercept of -2 and a slope of -2 as well. So from my first point, I'm going to go down 2, right 1 to use the slope, and graph my line. Let's discuss what this is telling us about the amount of solutions this system has. The first system, or our first problem, the lines intersected each other. Therefore, they shared one ordered pair, which is showing us that that would be the solution to both equations or to the system. For problem number 3, however, it doesn't appear that these two lines have any ordered pairs in common at all, since they do not intersect each other. In fact, we know that these two lines are parallel to each other and will never intersect each other since their slopes are the same. Since they have no ordered pairs in common, there are no ordered pairs that would be a solution to both equations. This is an example where we will write no solutions. There is not one ordered pair that would be a solution to both of the equations, therefore there are no solutions to the system. So far we saw one solution where the lines intersect, no solutions, that's where the lines are parallel, and the last option is when there are many solutions. Let's take a look at an example like that. We'll go down to problem number 5. As you could see again, the first equation is in slope-intercept form for us. We're going to graph it in pink and start at the y-axis at -3. We'll use the slope of 2 to now graph our second point or plot our second point of the line. Since it's positive, we will rise 2 and go to the right one and go ahead and graph our line. The second equation, however, is not in slope-intercept form yet. As you could see, the y is not alone. There's a 2 in front of it, or being multiplied to it. In this case, we need to do a little work on the side to write this equation in slope-intercept form. Since 2 is being multiplied to the y, we'll divide everything by 2 to get y equals 2x minus 3. Now that the equation is in slope-intercept form, we could graph it, again starting the y-axis at -3, and using the slope of 2 to plot our second point, where we're going to rise 2 and run 1 from our first point. As you could see, the two equations that we graphed were identical. They were actually the same thing, in which the two lines that we have on our coordinate plane are perfectly on top of each other. In this case, how many ordered pairs do they have in common? They actually have every ordered pair in common because technically it is the same line. Therefore, they have many solutions or many ordered pairs that would solve both of the equations. Therefore, this is an example where we would write our answer as many solutions. If they ask us to give us a specific solution, we can name any ordered pair that lies on both of the lines. Those are our 3 examples to show each 3 types of solutions you could get for solving systems of equations. What I'm going to ask you guys to do is pause the video, try the even problems. Once you get your answer, play the video back to double check. Here are answers for our even problems of graphing systems of equations. Problem number 2, when you graph the two lines, they intersect at one point, in which that will show us there is one ordered pair that's a solution to the system, or one ordered pair that would be a solution to both of the equations, being the ordered pair 1, 1. Second problem number 4, as you can see, they have the same slope and they're both in slope-intercept form. Therefore, when you graph these two lines, they appear to be parallel to each other. Parallel lines will never intersect each other, therefore will never have ordered pairs in common. This example will tell us that there are no solutions or no ordered pairs, that would be a solution to both equations or the system. And lastly, problem number 6, we did have to do a little bit of work since neither of these equations are in slope-intercept form. So over on the right, I'll rewrite the first equation, y minus x equals 2. How am I going to put this in slope-intercept form, or y equals mx plus b form? We need to solve for y. So what we're going to do is add x to both sides to get our equation y equals. We can write the right side as 2 plus x, but we know the x should go first, so we'll write x plus 2. Now that it's in slope-intercept form, we could graph by starting the y-axis at 2 and using our slope of 1 to make our second point, going up 1 unit and right 1 unit. The second equation, 2y minus 2x equals 4, I'm going to go ahead and write down below. And let's go ahead and put this in slope-intercept form. Just like the first equation, we're going to want to add the 2x over to get 2y equals 2x plus 4, writing the x term first. Differently from the first equation, the y is still not solved for since we have a 2 in front of it. Therefore, we'll divide the whole equation by 2 to get y equals x plus 2. As you can see, it's the same equation as the first one, where we'll graph a line right on top of our previous line. These two lines have every ordered pair in common, therefore we got our solution as many solutions. There are many ordered pairs that are solutions to both of the equations, since they are technically the same. Please let me know if you guys have any questions on our notes today, and I'll talk to you soon.